So in this video, we'll talk about a very important concept in error correction called fault tolerance, and we'll also talk about the threshold theorem. So roughly speaking, if you have a quantum circuit where the individual gate errors can be controlled below a certain threshold, and you make certain reasonable assumptions about the noise models, and also you implement your gates using a scheme called fault tolerance that we'll talk about, then you can bring down the overall error of the circuit below any epsilon error that you may choose. So this is the rough statement of the threshold theorem. Now let's see what happens without error correction. So if you are without error correction, then if you have S gates in your circuit, and each gate introduces an error with probability P, produces error with probability less than P, then one can show that the probability of at least one error in the overall circuit is bounded by S times P, provided we make certain assumptions about the noise. Now, this is not good enough because we want to reduce the overall errors of a circuit to below any epsilon value that we choose. So how do we go about doing that? Well, we have to understand a concept called fault tolerance. So let's go into fault tolerance. So the fault tolerance idea is that essentially if we implement a certain architecture using error correction and certain kinds of gates that act directly on the encoded states, then the errors don't propagate. And in fact, the probability of irrecoverable errors reduces at each and every level. So when can errors be introduced? So errors can be introduced during the encoding state part. They can also be introduced during the gates that act, and also during the measurement procedure. So we have to implement these fault tolerance schemes at each and every state. I'm mainly going to talk about the fault tolerance schemes that are introduced at the gate level. So firstly, as I mentioned, so there are two parts to this. So part one is that the gates, so we are going to restrict our fault tolerance to our gates. But as I said, that we should also talk about the measurement procedure and so on. So the first part of this is that the gates directly act on the encoded states. Right. So this reduces the possibility of errors being introduced during the encoding and decoding procedure, right? So for instance, if I have an X gate, which is we want to implement in the unencoded state, then this may be implemented in, for example, in a 3-qubit bit flip code. One can implement the logical X gate using 3 NOT gates. So this is entire thing is one logical X gate, right? And notice that it takes 0, 0, 0, which is our logical 0, to 111, which is our logical 1. And vice versa, right? It takes the logical 1 to logical 0. So the first thing about fault tolerance is that they directly act on the encoded states. The second thing is that implementation should be such that the errors don't propagate. And this is where we come across a scheme called transversal gates. So let's take an example of a C0 implementation. So C0 gate is in the unencoded state will look like this. There is a control bit. So there are two wires. One is the control wire and other is the target wire. Now, if I want to go to the error corrected scheme, if I look at the 3-qubit bit flip code, then this wire goes to 3 wires. And the bottom wire also goes to 3 wires. And one could have a control C0 gate implemented in the following way. You have X. So I have an X gate over here. And then X gate also over here. So the top wire is controlling the X gates on the bottom. So these are my control wires and the target. And notice that if I look at so I should have something which takes the logical 0, 0. So this is our C0 truth table, right? And so on, right? So 0L, 1L goes to 0L, 1L, and 1L, 0L goes to 1L, 1, and so on, right? So this 1L, 1L goes to 1L, 0L. Right? And notice that this indeed is the case, because if I take 0, so this will be 0, 0, 0 and 0, 0, 0. With this scheme, it does indeed go to 0, 0, 0, 0, 0, 0 and 0, 0, 0, 1, 1, 1 goes to 0, 0, 0, 1, 1, 1. None of the control wires are set. So this is 0, 0, 0, 1, 1, 1 goes to 1, 1, 1. And 1, 1, 1, 1, 1, 1 goes to 1, 1, 1, 0, 0, 0. That's a correct implementation of the control NOT gate. However, this is not a fault tolerant way of implementing because one error on the control wire, just the top wire, will propagate to wire number 4, 5, and 6. So the errors do propagate. However, if we implement the C0 gate in the following way, suppose instead of the above scheme, suppose we take the C0 implementation like this. So if I have 3 wires on the top, and instead of being controlled on just one wire, if we take the second and the third as well into account, then this scheme also implements the truth table of the C0. So this also implements. However, in this case, the errors do not propagate. So for example, if the error occurs on bit number 1, so if I take this bit 4, 5, 6, that only affects bit number 4, right? And there is another advantage of this. So if a single error occurs on any of the top bits, then it is still a recoverable error. only if more than one error occurs in the top two qubits do we have an unrecoverable error of this scheme. And that happens with probability order of p square. So the probability of an irrecoverable error. So in this scheme, now the errors don't propagate, and hence the probability of unrecoverable error is of order p square, right? So it went from uh, order p to order p square when we did the encoding and implemented this transversal gate scheme. So let me just define what is fault tolerant error correction. So let's assume that our error correcting scheme is capable of correcting one error. And so if individual gates introduce errors with probability p, then an implementation of a gate that directly acts on the encoded state is said to be fault tolerant if the probability of an recoverable error is bounded from above by Cp square for some constant C. So this is what our definition of a fault tolerant gate implementation will be. Similarly, we'll have the definition of a fault tolerant sort of measurement procedure and so on. So with this in mind, let's go to the threshold theorem. Okay, so third topic is threshold theorem. So for that, we need to understand what is known as concatenation code. So let's take an example of the 3-qubit bit flip code. So what we do in concatenation code is that suppose we have our initial logical 0 to be transmitted, then we transmit 3 zeros. So this will be level 1. Then in the concatenation scheme, we further concatenate these things to so this will be 0, 0, 0. So this will be level 2. This is level 1 of this 3-qubit scheme or bit flip scheme. This is level 2. So this is uh, so we'll implement the gates using these concatenation schemes also. Now, why do we do this? Now notice that if we use the fault tolerant implementation, if we have at level 0 error probability to be p, then at level, so this is level 0, level 1, using this fault tolerant procedure, we have Cp square, and at level 2, we have C times Cp square, the whole square, right? So this will be Cp to the power 2 square over C. In general, the error probabilities are going down. So at level K, so this is level K, it will be Cp 2 to the power K over C. So the errors are going down. In fact, they are going down very, very fast. They're going down doubly exponentially, right? So the gates that are being introduced in the fault tolerant way are reducing the errors doubly exponentially fast. And let's assume, so if we have a gate, if we have a circuit with, so a circuit with S gates, right? And we want the overall probability of error of the circuit to be below epsilon, right? Suppose we need overall error probability to be less than epsilon. Then if I focus on individual gates, then um, individual gate errors need to be below less than epsilon over S. Right? So but we are also adding a lot of gates, right? So the gates are, so how fast are the gates growing? For example, if I look at, for example, if I look at this, if I implement the X gate at the first level, there are 3 gates. If I do this one more time, there will be 3 square 9 gates and so on. So gates are sort of exponentially increasing at growing. So gates, so we have errors being introduced, and then we have gates. So errors, as we saw, are reducing. So these are reducing at C p to the power 2k, 2 to the k, and over C. And gates are sort of increasing at d to the k. Right? So there is a race between the errors being reduced and the gates increasing, but the errors are actually going down much faster. They are going down doubly exponentially. So this is doubly exponential, and this is exponential. So by using this inequality, so the inequality is that we want Cp 2 to the k. This is our individual gate errors. This should be less than epsilon over S, right? And what we see is that d to the power k, because of this inequality, is of order log of ms over epsilon. Right? This is because of this errors being sort of going down doubly exponentially and gates being going up exponentially fast. So the total number of gates that we need in our circuit is S d to the power k should be our order of S log of ms over epsilon, right? And the only thing to be careful about over here is that we need P, which is our individual component error, to be less than 1 over C. So P should be below this. Otherwise, this will not go down. So this P has to be less than 1 over C. And so what it says that if we implement this fault tolerant scheme, then we don't need that many gates because the errors are going down faster than the gates that we are adding. So with that, let me just write down the theorem, which is the threshold theorem. It says that a quantum circuit consisting of S gates can be simulated with probability of error less than epsilon with order of S log gates on hardware whose individual components introduce errors with probability P, provided P is below some threshold called P threshold. So that threshold is this value of 1 over C, right? So this is our threshold theorem, very, very important theorem in error correction and quantum computing in general.